When all outcomes of an action are equally likely, you can use the theoretical probability formula to find the probability of an event. The probability of an event equals the number of favorable outcomes divided by the number of possible outcomes. So in this example, we're spinning the spinner twice, and we're wanting to know how many times, or like what would our chances be of spinning the same color twice. So if we make a tree diagram, the first spin would give us options of red, blue, or green. And then the second spin would give us options of red, blue, or green again for each of those first original options. And 1, 2, 3 times out of the total 9 times, we would get the same color twice. So the chance of getting the same color twice is a 1/3 chance when you reduce. Remember, this is theoretical probability, so this is based on the design of the spinner, not actually running trials or running an experiment to see how many times it happens. That would be experimental probability. The table shows the possible outcomes of choosing one card from the group shown, replacing it, and then choosing a second card. Find each probability. So we do the favorable outcomes divided by the total number of possible outcomes. The probability of getting at least one apple. This one, any of these. So we can see that that is, let's see, 9 chances to get at least one apple out of 5, 5, 5, 25 total possibilities in the whole table. And we can't reduce that, so we would leave it like that. The probability of getting exactly one apple would be 8 out of 25, which you also cannot reduce. The probability of getting exactly one apple and one fish. Looks like 2 possibilities out of 25. And again, you cannot simplify that fraction any further. The probability of getting at least one apple or fish. So we want at least an apple or at least a fish. That has a fish or an apple. All of these have a fish. All of these have fish. All of these have at least one apple. So it would be all the chances to get at least an apple or at least a fish. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 chances out of 25 total possibilities in the whole table. Alright, it's a good time to pause the video and see if you can answer this question, and then play the video to see if you did it right. In this example, we have a tree diagram instead of a table, and we have the possible outcomes of choosing a card from the group, setting it aside, and then choosing a second card. So you can see that, once you draw the fish, you can't draw the fish again. So they're taking the card out this time, so our sample space has changed. We want to know what's the probability of getting at least one fish or one apple. Well, this would be a fish with a star, so that at least has a fish. This has a fish, fish, fish. This one has a fish, and this one has an apple. This one only has a shark and a key, so that doesn't work, and has a shark and a leaf. All of these have apples, because they start with the apple on the first card. This one has a fish. Okay, in this category we have an apple. Here we have at least one fish or at least one apple. So if we count all of our checks here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 chances to get at least one fish or one apple out of 4 times 5, 20 chances. We want to reduce. We could say the chance is 7/10. Okay, in this book, you can arrange the eyes, nose, and mouths of the 3 people in various combinations. You choose a combination at random. Use an organized list, a table, or a tree diagram to find the probability that your combination shows exactly 2 parts of the same person. Well, I'm going to use a tree diagram. I think that'd be easy. We have 3 choices to make. Someone's eyes, someone's nose, and someone's mouth. So I'll organize my tree diagram like that. And rather than worrying about their names, I know I have 3 people, so I'll just say person 1's eyes, person 2's nose, person 1's eyes, person 2's eyes, or person 3's eyes. Then when you choose the nose, you could choose the same person's nose, or person 2's nose, or person 3's nose. Same thing for all of these people. And when you go to choose the mouth, even if you choose person 1's eyes and person 1's nose, you can choose person 1's mouth, or 2, or 3. So each of these would branch out into person 1, 2, or 3. I should have spaced my tree diagram out a little better, but it'll work. Okay, so we want to know what's the probability that 2 parts of the same person are used. Well, if we travel this first path, we're using the first person's everything. So that's at least, or no, it's supposed to be exactly 2 parts. Okay, so that wouldn't work. This uses person 1's nose and person 1's eyes, but person 2's mouth. So that would fit. This one, same thing. We're using person 1's eyes and nose. That'd be exactly 2 parts of the same person. This one uses person 1's eyes and mouth, person 2's nose and mouth. And that one's all different. This one's person 1's eyes and mouth, person 3's nose and mouth. Let's see, this would be person 1's nose and mouth, person 2's everything, person 2's eyes and nose. I'm just following each path. Person 2's eyes and mouth right there. Person 3's nose and mouth. Let's see. Exactly 2 of the same person. Be that eyes and mouth for person 2 and nose and mouth for person 3. There's one right there. If I squeeze it in. One right there. Or no. That one I messed up. Those are all different. And then this one has person 3's eyes and mouth. Person 2 has 2 there, and person 3 has 2 there. And those 2 would work as well. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 times that we got the same person's just 2 parts exactly from the same person and 1 part different. Out of, if we count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 total different faces that you can make. You can reduce, well, by 9 even. and it's a 2/3 chance or 2/3 probability that you get exactly 2 parts of the same person. Alright, again, this is a good time to pause the video, try it out on your own, make sure you get the right answer, and play the video to correct any mistakes or verify your work. Alright, in this one we are going to pick a geography fair partner and a country at random. So they're just put in these boxes. We have to draw one from each box. Use an organized list, a table, or a tree diagram to find the probability of choosing your best friend, Miguel, and your favorite country, Grace. Well, this one has 2 steps or 2 choices that we have to make, and I kind of like to use a table if I have 2 choices. Okay. You could also do a tree diagram. Okay, so in my table, I have to choose the names: Nora, Miguel, Otis, Priya, or Quincy. And I have to choose a country: Ethiopia, France, or Greece. So I could choose Nora with Ethiopia. I could choose Miguel with Ethiopia, Otis with Ethiopia, Priya with Ethiopia, or Quincy with Ethiopia. And I could choose each person with France. Or I could choose each person with Greece. So by filling out this table, I am displaying my sample space possibilities, and it allows me to answer a lot of questions about the situation. It also allows me to see all of the possibilities in an organized way. Alright, so we want to know, what's the probability of choosing your best friend Miguel and your favorite country, Greece? If we want Miguel and we want Greece, there's only one chance for that to happen out of, let's see, 15 total chances. So the probability of getting Miguel and Grace would be 1 out of 15. You can use the probability tool to run trials of a 2-step action and to compare experimental probabilities to theoretical probabilities. Remember that experimental probabilities are based on trials or an experiment. You actually run the event, or you run the action and see how many times you get your event. And theoretical probabilities are like what we expect to happen based on the way that maybe the spinner or the hat of names or the coin or whatever it is that you're using is designed. To get an experimental probability, we would say that we would take the number of times the event occurs divided by the total number of trials. So it's very similar to theoretical, but it is based on trials, or what we call an experiment. A class ran 330 trials of this 2-step action, tossing a coin once and spinning the spinner once. Complete the table for which compound event is the count closest to the expected count. So here in our table we can see that they got heads with red 45 times, they got heads with blue 59 times, and you can see all the times that they got each one. The experimental probability would be how many times you got that event divided by the total number of times that you tried. So we would just need to make sure we reduce each of our fractions. I'm going to pause the video at this point and go on to part 2 of the video to finish the lesson.